Okay, so once again, let me go back and show you the enrollment information just in case the people online didn't see it last time. So to get into this thing, you'll have to use this class key right here at webassign.net. Friends 70711008. Okay, now let's go back to this view. So this is what you'll see as a student. And then we already went through these last time. Let me turn down the lights. And by the way, you have to get this review done, and then you can take the final. It's going to be an in-class final for the on-ground students and an online final for the online students. But you can't obviously take the online final unless you're one of the 3 students who's actually an online student. There is absolutely no option to do that. But if you get a good enough grade on this review, like I said last time, now technically it's only for the people that were there last time, but I might be willing to let other people do it as well. But if the average of the people that was here last time is at least 90, then I forgot exactly what I said. Did I say that you didn't have to take the actual final then? Okay, yeah. So then you don't actually have to take the final because you did well enough. But then later on, someone was talking to me in my office and said, well, what if I get everything right and then somebody else causes it to be under 90? So I went ahead and I decided to say if somebody gets every single thing perfect, every single part of every single problem completely right, and there's nothing that they can do better, then you won't have to take the final and then I'll use your grade for the review for the final grade for you. But that's only if you get everything perfect. Otherwise, you can only skip the final if the average is above 90 for the people that made that deal with me last time. So, and the people that didn't make the deal with me last time, they're just on their own, basically. Okay, so now let's go ahead and continue on. So let's go to question number 8. Find a formal negation for each of the statements. So what's the negation for this statement? For all string, now it should say strings, but for all strings S has at least one character. What's the negation of a for all?
Exists.
Yep. And so the negation of for all, and then a proposition is there exists something that it's not true that that proposition happens, right? So what's the negation of that something has at least one character? Right. So that means that there exists a string such that S does not have any characters. So it'd be that one. Perfect. Okay, what's the negation of for all computers? The computer has a CPU. What's the negation of for all computers? The computer has a CPU.
There is a computer that does not have a CPU.
Yep. There exists a computer that does not have a CPU. Right. Perfect. And then what's the negation of there exists a movie that is over 6 hours long? What's the negation of there exists a movie that is over 6 hours long? What would the negation be? So let me just check off the attendance real quick. Amani, America, LaShawn, Shamarius, Anthony, Zoe, Olivia, Isaac, are you here, right? Okay, perfect. Um, now Anthony Johnson. Okay, Colin Morrison. Here. Good job. Sorry, my pen's broken. There we go. Ignacio, you here? Okay. Caleb. Are you here, Caleb? Arturo, you are here, right? Okay, good job. Taylor, okay. Logan, good job. Mercadia, good job. Perfect. Okay. So what's the negation of there exists a movie that's over 6 hours long? It would be for all movies, they are what?
Underused.
They're less than or equal to 6 hours long. Yep. So for all movies, it's less than or equal to 6 hours long. What's the negation of there exists a band B such that B has won at least 10 Grammy Awards? It'd be for all something. It'd be for all bands they have not won at least 10, which what's the negation of not at least 10? What?
Fewer than 10.
Fewer than 10, right? So they're for all bands they have won fewer than 10. Yep. There we are. Okay. And then we did this one already, but let's go ahead and do it again just to make sure we get through them all. So I'll let you help me figure this one out. So if b mod 12 equals 5, that means that b itself is a multiple of 12 plus a remainder of 5, right? So 5 would go into that box, right? Multiply both sides of this equation by 4, right? So if you multiply the equation by 4, you get 4b equals 48m plus 20, right? So 4b equals 48. Okay, I wish I had some scratch paper to write on. That's what the board is for, though. So if I take that equation, b equals 12m plus 5, you get 4b equals 48m plus 20. Now you have to help me do this, or else you won't. That's why I'm doing this together, so that you can help. That's the only reason, that's the only way that you can get to do this instead of the final. So I need to express this as a multiple of 12 plus a remainder, right? So does 12 go into 20 at all? One time, right? So this is equal to 48m plus 12 plus a remainder of 8, right? So that means that if I factor 12 out of this, you get 12 times 4m plus 1 plus 8, right? So then it says to find the values of what number is beside the 12. 4b equals 12 times what plus what? So it equals, let me turn on the slide so you can see this a little bit better. Or it's in the dark. Okay, there we go. So 4b is equal to 12 times, so q is, which number is q? The one beside the 12. 4m plus 1. And what number is left over?
8.
8. Correct. Now, since q is an integer because products and sums of integers are integers, so the uniqueness part of the quotient remainder guarantees the remainder obtained when 4b divided by 12 is 8, right? Okay, by the way, let's submit these other answers. I'm not sure if you submit them all at once or if you just submit them one at a time. Perfect. So you'll have to figure out your one on your own because you might have different numbers, possibly. And then just do not submit this one at the same time. So let's submit that one. So you see, it's very easy to understand, but you have to use your brains to think about it. It looks impossible when you look at it first. Turn on your brains, then it's very, very easy. Perfect. Okay. Now let's do this one. So this one is not written in a linear fashion like I like to do, but let's work on this loop though. So there's the K value. The first thing the computer does is not to set up a table. It just does things one at a time. So the table is like an illusion. But the first thing the computer would do is to set E equal to 4, and then it set F equal to 0. The third thing the computer would do is to set K equal to 1, right? So do you see how that before K is set to anything, E is already set to 4, and F is set to 0. So that first column represents the first two assignments the computer would do. and I hate these tables because they're not written in linear fashion, then they give you they don't actually show you how the computer thinks. But that's just that saves space so that they have, you don't have to use a whole page full of numbers. Then the next thing the computer does is it sets k equal to 1. So right here, k is equal to 1. And then after k equals to 1, e equals what? E is equal to itself times k, which is 1. So e is going to equal itself times 1. What's 4 times 1? 4. Correct. And then f is going to equal e plus f itself. So f right here, f itself is going to equal what e is now plus what f was previously. So what's 4 plus 0? 4. Correct. Now you're going to k. Now what happens, the computer really sets k equal to 2 next. So that top of that line, that's the next thing the computer does. So k is going to equal to 2. And then e is going to equal itself, whatever it was previously, times k. So e right here is going to equal what it was previously times k. So what's 4 times 2? 8. Correct. And then f is going to equal what e was previously plus f itself previously. So f is now going to equal e previously plus f previously. So what's 8 plus 4? Correct. Now I've got a question. I feel like something's wrong with this because don't the numbers in these problems change to red if they're different?
No,
They don't?
because I did like half this and it was.
It's not the same?
Okay, no.
Okay, good. Okay, because usually when I use WebAssign for like calculus classes and other classes, when the numbers are different, they're in red. Do you know what I mean? Like if you've ever had a calculus class, the numbers are different in red, but I'm noticing none of these numbers in red. So I'm just hoping that I'm not doing all of your questions for you, but I'm not, I guess. So okay. So let me just look at something real quick. Because I printed out one and it should have different numbers randomized. Well, actually, this might be the same version though. 12M. P mod 12. Okay, yeah, it is different numbers. Okay, so I guess they got rid of the red color. Okay, then K, the next thing the computer does is set K equal to 3, right? Perfect. And then once K is equal to 3, the next thing the computer does is set E equal to itself times K. So it sets K equal to 3, and then it sets E equal to its previous value. E is equal to its previous value times the K value. So E is equal to 8 times 3. What is 8 times 3? 24. And then F is equal to E's previous value plus F's previous value. So F would equal to 24 plus 12. What's 24 plus 12? 36. Correct. So we're done with that. Now, after it's done, nothing else happens after it's done. The computer just stops thinking. So the E would be left as 24 and the F would be left as 36. Perfect. Okay. Now, prove the following using mathematical induction. So the first thing you have to do, remember there's 3 parts. You have to prove that the first case is true. So it says that this statement is supposed to be proven for every integer bigger than or equal to 1. That means the first case would be 1. So we need to show that case number 1 is true. And case number 1 is the statement that the summation of all these fractions until you get to 1 over 1 times 1 plus 1 is equal to 1 over 1 plus 1, right? So that would be a very simple sentence. It would just be 1 over 1 times 2 equals 1 over 1 plus 1. So it'd be 1 over 1 times 2 equals 1 over 1 plus 1. It'd be this one, right? So that would be the statement P of 1. And is that a true statement or not? Yeah, because it'd be 1/2 equals 1/2. Then we need to assume, now this actually skips a step. Technically, the second step is to assume the statement P of K is true. So if P of K is true, then P of K would be which of these statements? The left side of PK. It'd be this one, right? Let me just double check. P of K would be 1 over 1 times 2 all the way through 1 over K times K plus 1. So it'd be 1 over 1 times 2 plus that all the way through 1 over K times K plus 1. Yep, that'd be it. So now the right side of P of K is what? If I plug K into this right side, what would I get? You get what? What would you get? K over K plus 1, right? K over K plus 1. Perfect. Okay, perfect. Now, we must show that P of K plus 1 is true. P of K plus 1 is the equation what? What is the equation P of K plus 1? Well, it'd be this equation. Everything starts with this equation, right? But it go until n equals K plus 1. So what is K plus 1? K is K plus 1. What is K plus 1 plus 1? If I plug in K plus 1 for n, what is K plus 1 plus 1? Yeah. So it'd be K plus 1. In fact, they don't even have you even plug in K plus 1 plus 1. They just let you do it as K plus 1 plus 1. Okay, and then that would equal, if I plug in K plus 1 into the right side, what would I get for n? K plus 1. If I plug in K plus 1 on the bottom, what would I get for n? K plus 1. And then you have K plus 1, which is K plus 2. So you have K plus 1 over K plus 2. K plus 1 over K plus 2. Boom. Perfect. Which of the following choices results in applying the inductive hypothesis to the expression on the left-hand side? So what is the inductive hypothesis? The inductive hypothesis says that if you add all the terms in this pattern together, all the way up to the K term, that you'll get K over K plus 1, right? So we could take this entire expression right up there and replace everything before this last term with just the expression K over K plus 1. So we would get K over K plus 1 for all of these other parts plus this one fraction at the end. So we would get this first answer. So there we go. And then when the left-hand and right-hand sides of the statement, so here's the left-hand side of that statement after applying the inductive hypothesis to it. And here's the right-hand side of that statement after applying the inductive hypothesis to it. So if we simplify this left-hand side, which I put the dot beside, and if I simplify the right-hand side, what do I come up with? Well, let me turn the light back on. You can't do that in your head. You have to do algebra. So the left-hand side is the part with the blue dot beside it. So it's K over K plus 1 plus 1 over K plus 1 times K plus 2. So do algebra to that. So pretend like this is actually intermediate algebra. So remember, how do you add fractions together in intermediate algebra if they don't have the same denominator?
You have to multiply whatever's in the bottom to make them.
Yep, whatever's missing on the bottom. So in my class, I said that this is like a one kind of sports car, this is another kind of sports car, and this is the neighbor, and this is the other neighbor. So this neighbor is going to be jealous of the K plus 2 sports car, and they're going to want one. But when you multiply by something in the bottom of a fraction, you have to multiply the top of it by the same thing. So now they both have the same things in common in the denominator. That means you can join them together into a single fraction. So if you join them together, you just get the top of this plus the top of that. You just get k plus 2 times k plus 1 over the bottom, which is, now technically I could say k plus 2 times k plus 1, or I could say k plus 1 times k plus 2. I'm going to just start the smaller one first. Because one number times another number is the same as the other number times the other number. The order doesn't matter. Okay, so there's the simplification, but I need to do a little bit more than that though. I need to multiply at the top. So if I multiply at the top, I get k squared plus 2k, k squared plus 2k plus 1 over k plus 1 times k plus 2. Now I need to factor the top. So remember, factoring is in like intermediate algebra as well. So what does the top of factor out to be? What does the top of a factor out to be? What two numbers multiplied equal 1 that add up to make 2? 1 and a 1, right? The top factors into k plus 1 times k plus 1. The bottom is already factored. And now which two factors cancel? That one, right? So it equals k plus 1 over k plus 2. So the left-hand side of the problem simplifies from these two fractions into one fraction, k plus 1 over k plus 2. But k plus 1 over k plus 2 is also what the right-hand side simplifies to equal. So both the right-hand side and the left-hand side both simplify to equal k plus 1 over k plus 2. Boom. Therefore, it's true. And therefore, why did this thing get in the way of my screen? Can't even read the, okay, there we go. Can't even read the problem with that thing there, which completes the inductive step. So that's done. So let me dim the light again. So this next one, we've already gone over this before for the last test, and I think we've even done this before in the final review anyway. So let's just skip this one. I'll let you figure that one out by yourselves. And then let's go ahead to this one. Consider the following recurrence relation and initial conditions. Supposing a sequence of powers of t satisfies the relation, what's the characteristic equation? So we've already learned how to do this before. You start with the smallest index of the term, which in this case is bk minus 2, right? You replace bk minus 2 with 1. I'll put it in parentheses to highlight it. And then you put negative 14 in front of it. Then you look for the next sequential index of bk, which is bk minus 1. You replace that with the variable t. We said r, but this is saying to use t. Then you put the equals in front of that, and then you replace the next index of b, which is bk, with t to the next power, which is t squared. So the characteristic equation of the recurrence relation would be t squared equals 9t minus 14 times 1. What are the possible values of t? So we have to solve that. So I'm going to solve this for you on the screen, and then I'll delete my work. I'm just going to use that box like a piece of scratch paper. So it's t, so ignore the t in front of it. So the first step would be to say t squared minus 9t plus 14 equals 0, right? What did I do in that step? I set it all equal to 0, right? The next step is I need to factor the left side. So what factors would fill out the left side? T and what? T and what times t and what? Yeah, -2 and -7. Exactly. And that would equal 0. And then if I set each of those factors equal to 0 by themselves, let me put another fraction in the bottom of that. I'm using the fractions like a step to like separate the steps. If I set each of those equal to 0, if I do t minus 2 equals 0, what's the solution to t minus 2 equals 0? 2. And what's the solution to t minus 7 equals 0? So t equals 2 and 7. So I'm going to delete all the work now because you've seen it. Is everybody watching? Okay, I'm going to delete all the work now because you've seen it, and it's 2 and 7. Those are the solutions. Now I suppose a sequence of numbers satisfies the initial conditions. Fill in the blanks below to derive a formula for it. Okay, so it follows from part A, and I actually don't know the name of this theorem. Probably the distinct roots theorem. That for some constant C and D, the terms B0, B1, B2 satisfy the equation Bn equals C. I don't know why that thing gets in the way. Whenever I'm typing in a box, that calc pad pops up and hides the box. Isn't that the stupidest web design ever? And I can't obviously see what I'm typing or do anything else. I'm just going to zoom out. Maybe then it'll work better. I wish that the designers of this web page could see how dumb it is. By the way, if you're ever designing web page, keep in mind things like that. Don't have pop-up things come in front of people that go in front of the actual thing that they're trying to type into. Because that you might be doing that job in the future. So just remember this lesson. That might be the most valuable thing you learn in this class today is just that little thing. So Bn equals C times root number 1 to the power of n plus another constant D times root number 2 to the power of n. Not 2, I meant n. So Bn equals C 2 to the n plus D 7 to the n. Solving for D, C, and D by setting up a system of two equations. Now this has a lot of work to do. You're going to have to know how to do this. And I don't know if I can trust for you all to know how to do it. So let me do this on the board. Or actually, I can do this on the whiteboard. That'd be easier. Because I have the whiteboard right here. So this way online people can see it as well. So ready? I'm going to make sure you have that written down in your notes, and I'm going to switch to a whiteboard. Ready? Okay. So first thing is I'm going to write down the equation. Whoops. I'm going to write down the equation, which is Bn equals C 2 to the n plus D 7 to the n. And then it said the initial conditions were B naught equals 2 and B1 equals 0. So let's switch to this, make it full screen. And then let's solve the necessary equations. So basically what we know is that if we put in 0 for n, we'll get this equation. If we plug in 0 for n, we'll get B0 equals C 2 to the 0, which is 1, and set D times 7 to the 0, which is also 1. So if we put in 0, that's what we'll get. We also know that if we put in 1 into that equation, we'll get B1, which would be C times 2 to the 1, which is just 2. Oops, I meant to say C. My brain's always one step ahead for some reason. C times 2 to the power of 2. No, 1. Sorry. I'm plugging in 1 for n, so it's 2 to the power of 1 plus D times 7 to the power of 1. But the power of 1 doesn't matter, so I'm just going to delete the 1. So that's what you get if you plug 1 into the equation. But I know I'm given prior information from the problem that says B naught or B0 is equal to 2. So I can erase the B0 and I can erase the B1 and I can replace B0 with 2 and I can replace B0 with B1 with 0. So then I have a system of equations to solve. This is just like another intermediate algebra problem. Have you ever heard that everything you need to know in life you learn in kindergarten? Well, in this class, it's more like everything you need to know you learn in intermediate algebra. Sometimes I wonder why don't tell that to the other people, but intermediate algebra is probably actually more important than college algebra, to be honest, because that's where the actual true algebra is taught. So 2 equals C plus D. 2 equals C plus D. 0 equals 2. Oops, I made a mistake. What mistake did I just make? Correct. Right. So 2 equals C plus D and 0 equals 2C plus 7D. How do I get rid of a C or a D? it'd be easier to get rid of the C because there's just 2C, but there's 7D. A good way to get rid of the C is to multiply the top equation by -2, because then the top equation will be an opposite to the bottom equation. So then you get -4 equals -2C minus 2D. Remember, this is what true critical thinking actually is mathematical, logical thinking. Well, not just mathematical thinking, but logical step-by-step thinking and problem solving. That's the real thing that they're trying to teach you in math and everything else is problem solving. So set up the problem, then figure out how to solve it and get what you want. So we get -4 equals 0 plus 5D. Divide by 5, and you get -4 over 5 equals D. So that was easy. -4/5 equals D. But I need to know what C is as well as what D is. So what is D? I mean, what is C? I mean, how do I find C? Well, the easiest way to find C is to use the easiest equation, right? So there's the easiest equation. 2 equals C plus D. Let's use that. 2 equals C plus D. You'll get 2 equals. Now, the frustrating thing is, I know you can probably just like point your AI thing at this and just get all this work done. But that's up to you if you really want to be a good person or a bad person. So 2 equals C, which I don't know, plus D, which is -4/5. So 2 plus 4/5 equals C. So what's 2 plus 4/5?
It's 14, guys.
Yep, 14. Oh, sorry, I said 10. 14/5. So 2 is the same as 10/5. 10/5 plus 4/5 is 14/5. So you get 14/5 equals C. So that means the solution is I circled it at the top. Okay, so is it okay if I just go back to the top again and erase the C, right? What do I put in for C? 14/5. 14/5. And then I'm going to erase the D. And what do I put in for the D? What?
-4.
-4/5. Right. So 14/5 times 2 to the n, minus 14 minus 4/5 times 7 to the n. So Bn equals 14/5 times 2 to the power of n minus 4/5. Now what you're doing when you're solving these problems is extremely important because recurrence relations are very powerful. Very amazing things. They allow you to have a closed form solution for what's basically an infinite problem. So there's that. Let's just double check the answer. Perfect. Okay, good job. Now let's go ahead. Yes.
Quick question about the review. Are we able to do a question this many times?
Yeah, I believe so. If you submit the answer, you can just submit it again and again. I don't think there's any limit on how many times you can submit the answer, unless I'm wrong. Have you submitted one and it didn't let you submit again? Let me just try it. Let me put in like X for that. Submit answer. So it's wrong. So you can now change it to like 7 or 4 and you can try again. You can keep submitting. Now there might be some limit because of the programming. It might say like 99 tries is the limit or something like that. But it's basically unlimited as far as I know. So you can try it again if you get it wrong. Yep. Okay, now let's do this one. Let A, okay, let me clear the screen and reshare the main screen. Let A, okay, let A equal ABC and B equals BCD and C equals BCE. And try to find these sets right here. Now, by the way, here, there's the person who helped first teach people things like this. He was a very good teacher, and his name was Leonard Euler as well. I think I've mentioned him before, but he went blind eventually because he liked everything. He works probably because he worked so late on math, and back in those days, they just had candles and things like that. Imagine trying to do your homework with a candle all night long. That would be horrible. Well, you know what? I better not do it on the board because then people can't see it online. Okay, so what we're gonna do is we're gonna draw a diagram of this on the whiteboard. So A, B, C, B, C, D, and okay. A, B, C, B, C, D, B, C. Actually, I think everybody does have the same question on this one, I believe. Because my randomized version is exactly the same. I think this is the same for everybody. So maybe you should actually skip this one because I actually have done this one before. Remember when we started reviewing the final in the past? I actually did this one before.
I don't think you explained how to do the last,
The last part.
very last one, like the negatives, because I didn't know how to do that one.
Oh, okay. That means that's called the set minus. When you have a set minus a set, that means set minus. And that means that you take out from the set whatever is in the other set. So I can do that part. So let me go ahead and share my screen. So share whiteboard, continue, classic, view full screen. Oh, I guess it is full screen. Okay, there we go. So I'm going to draw a diagram like this. This is the way that one of the smartest people in the universe taught these problems. He drew a box around everything that represented the universe. That box represented the universe. And then he drew a circle called A, like this. That was called A. And then he drew a circle called B that kind of overlapped. And he drew a circle called C. Have you ever seen things like this? Okay. And then he put the things inside of those circles that belonged in them. And A is equal to ABC, B is equal to BCD, C is equal to BCE. So actually, I should have made this a little bit bigger, but B and C are in the middle of it. B and C are in common to all the sets. A is equal to A and B and C. B is equal to B, C, and D. And C is equal to B, C, and E, like that. Do you see that diagram? So that when you diagram the sets like this, it makes it easy to answer all of the other questions very easily. But let's go ahead to part C. That was the part you couldn't do, that we didn't do together, right? Does everybody else agree with that? So let's look at part C. Part C of this question says to find A minus B minus C, right? Okay, so A minus B, that means everything that's within A minus everything that's inside of B. So what's inside of A is A, B, and C. Minus what's inside of B is B, C, and D. So basically I cancel out the B's, cancel out the C's. Now you can't subtract a D out of an A because a D, there is nothing to actually take out. So basically the set minus operation takes anything that's in this set out of that set. But if there's something in this set that's not in that set, it's already out of it, so it doesn't have to do anything. So the only thing that's left is just the letter A. Okay. So the answer to that is just simply just A. And you can put the little brackets around it to mean it's a set containing A. Then the next step in this question says, what is A minus parentheses B minus C? Well, now the parentheses are in a different spot. So A is still equal to ABC, right? Minus B is equal to BCD, and then minus C, which is equal to BCE, right? So if you minus the B, C, and E letters from the B, C, and D letters, B's would be canceled, C's would be canceled, and you can't really cancel a E out of a D because there is no E in the D. So the only thing left is just D from that one. So it's A, B, C minus D. Well, you can't really cancel the letter D out of A, B, and C because D isn't in it. So the answer is just A, B, C. So that's the answer to that. And then it asks you, are those sets the same as each other? So is the set A minus B, parentheses minus C, the same as the set A minus parentheses B minus C? No, they're not the same. So that's the result of that. Okay, so the rest of it, I'm just going to leave you with the one that I did before. Let's move ahead to the next question. Share Windows. There we go. Okay, functions f and g are defined by the following diagrams. Yep, that's the next one. So f maps 1 to 3, 3 to 1, and 3 to 5. G maps 1 to 1, 3 to 1, and 5 to 1. Now, which of them defines f circle G? So I'm going to use my mouse. Hold on, the mouse is too small for you to see clearly in the video. So I'm going to type in the cursor settings, and I'm going to see if I can make this cursor bigger. Pointers. Hold on. Cursor size. There we go. Mouse pointer size. There we go. Okay, how's that? And now let me change it to like, there we go. Okay. So now that's a little too big. Okay. It still looks super small on the recording. I don't know. Like on the recording, it looks like that big, but okay, so functions f and g are defined by the following arrow diagrams. It looks a little bit bigger, but that helps. So which defines G circle F? I'm just going to use this because that thing is too complicated. So which defines G circle F? In other words, the G circle F means F comes first. I know it looks like it comes last, but it actually comes first. The X values get plugged into. So let's say you have an X value, you're saying G of F parentheses of X. The X gets plugged into F first and then G. So if the number 1 gets plugged into F, the number 1 is going to map to 3, right? And then the number 3 gets plugged into G. This is also, I'm not sure if this is intermediate or college algebra, but it might be college algebra, but it also gets plugged into G. But notice G takes every value that's input always equals 1. So actually, once it gets plugged into G, every single thing is going to go towards 1. So actually, the final outcome is going to be 1 no matter what. So that's an easy answer. So the answer is this one. Boom. But now the other way is not going to be so easy, though. Actually, it maybe will. Because no matter what X value you plug into G, it'll always become 1, right? So 1, 2, or 3, every value that you plug into G always becomes 1. And then when you plug that into F, F of 1 equals what? What is F of 1? F of 1 is equal to F of 1 equals 3. So everything you get out will always be 3. So the final result after doing F circle G is always going to be 3. That one. So every single value is going to become 3. So that's amazing. Because what F of G means that you plug an X into G first, which makes it become 1. And then you plug that result into F. And then you get 3 for the answer. Do they equal each other? No, they don't, right? This answer right here, this answer does not equal this answer. Perfect. Okay, well, we only have 2 minutes left, but that's pretty easy. So there's 4 points, there's 4 vertices in this relation, and the relation relates A to B and A to C. So from point A, there's going to be 2 arrows coming out, going to B and going to C. And then B is going to be going to C. So let's look down real quick. Let me zoom out a bit so you can see them better. So we need an arrow that's going from A to B and a loop that's going from D to itself. So is it going to be this answer? No, that's not that answer. How about this answer? Could be this answer. Let's just check. Hold on. I think there's more answers. Maybe not. Oh, wait, there are more answers. There's lots of answers. Okay, sorry. This is actually an answer. This is an answer. So there's no more than 3. So it's not that one. It's wait, where is D though? So D should have a loop coming to itself. A should be going both to B and to C. So A should be going to B and to C, right? And then B should be going to C as well. But then D should be going to itself. So I think it's this answer, but the formatting of this website's messed up. So I can't tell for sure whether this D right here is part of the second one or the part of the first. Okay, oh, there it is. Do you see that box that went around it? It is part of that one. So this is the correct solution right there. Okay, well, that's all for today. So we're going to keep on continuing in the review next time. We only have 15 more questions to do on it because there's 31 in all. So remember, if you get a perfect score on the review, then you don't have to do the final. But if you don't get a perfect score, then you have to get that class average test, or whoever was made the deal with us has to have an average of at least 90% on the final, or else you will have to take the final. So basically, the easy way not to take the final is to get a perfect score on the whole review. And remember, if you need to get into the review, I've said this a lot of times, but if you missed it every time, the class key for getting into the review is to go to webassign.net and log in with this class key friends 70711008. It's free for 2 weeks. So you have up to 2 weeks to finish the review. So any questions? And by the way, before you leave though, hold on, let me just do attendance real quick.